Good morning, everyone. Welcome to Season 3 of the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we'll have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
And in today's episode, our opener is Yingying Ren, and she's going to talk about 3D weaving with curved ribbons. And our headliner, Jing Ren, is going to talk about non-rigid shape matching with functional maps. And if you have any questions, please leave comments on the YouTube or our Discord channel. So first, it's my great pleasure to introduce our opener, Samara. So she's a PhD student at EPFL, supervised by Professor Mark Poley, and she's really a rising star who already has many experience in several topics. She's definitely a geometer, but she also touched topics like robotics, virtual reality, deep learning, and also studied one of the most delicious theorems, the ham sandwich theorem. But unfortunately, today, she's not going to talk about hams and sandwiches. Instead, she's going to talk about 3D weaving, which is another multidisciplinary problem, which involves like physics simulation or optimization or some differential geometry. So without further ado, please join me to welcome Samara.
Hi, thank you so much for that introduction. I'm really happy to talk to you about my recent work, 3D weaving with curved ribbons. Actually, let me share my screen. Just so that go through that. Okay, now I should be able to see the slides. This work is inspired by the art of basket weaving. I had the great honor to work with the amazing weaving artist, Alison Martin. Everything started when she had too many bamboos growing around her house, and she processed the bamboos into straight ribbons and built amazing bending active woven structures like this one shown here. Bamboo is one of the traditional weaving materials. With the help of digital fabrication, we can easily produce ribbons of arbitrary shape using many different types of materials. In this case, if we fabricate a set of planar ribbons from the right and weave them, we'll get this woven bird. We were able to produce a wide range of woven geometry by optimizing the ribbon's planar shape. And I'll explain how it works, starting with the basic principles of basket weaving. Here's the classical triaxial weaving pattern. With this regular pattern, the woven patch is flat and can be deformed as a developable surface. To obtain doubly curved surfaces, we need to take a closer look at the geometry. Most of you are probably familiar with the Gauss-Bonnet theorem, which connects the curvature of a surface with its topology and boundary. Even though we do not explicitly apply this theorem in our optimization framework, it's very useful for understanding why the optimization works. The M in the equation is the surface domain. Let's consider the boundary of M to be this hexagon. The right-hand side of the equation is simply 2 pi times the Euler characteristics of the surface. The Euler characteristics only depends on the topology of the surface domain. For example, any shape with a spherical topology has Euler characteristic 2. The torus topology is 0, and in our case, the disk topology has Euler characteristic 1. So as far as we're concerned, the right-hand side is always 2 pi. Next, the first term on the left-hand side is the integral of the Gaussian curvature over the surface domain. The Gaussian curvature is an intrinsic property of the surface. For example, the sphere has positive Gaussian curvature everywhere, and the saddle shape has negative Gaussian curvature. To build woven structures of arbitrary shape, we need to control the integrated Gaussian curvature of each cell in the weaving pattern. And we do that by using the second term, which is the integrated geodesic curvature along the boundary. In our case, the boundary is made of 6 piecewise smooth curves. So we can separate these terms into the integrated geodesic curvature along each curve and the sum of all turning angles between the curves. In particular, we're using straight ribbons in this regular patch, so the geodesic curvatures are 0. The turning angles sum exactly to 2 pi, so this cancels out with the right-hand side, which leaves that the integrated Gaussian curvature is 0, and that matches with what we started with, a planar weave. By now knowing this relationship, we can start getting more interesting patches. If we start with this regular pattern and push the ribbons around the middle hexagon further apart, we'll decrease the turning angles, and that results in a positively curved patch. Similarly, if we push the ribbons closer, we'll increase the turning angles and results in a negatively curved patch. Varying the ribbon spacings allows us to control the surface curvature to a certain extent, but at some point, the ribbons will collide or become too far apart. A different way to drastically change the sum of turning angles is to insert topological singularities. Here, if we cut one side of the hexagon out and stitch the two new boundaries together, we'll reduce the sum of turning angles by pi/3, and hence the surface become positively curved. If we instead insert a new section, and hence increase the turning angle by pi/3, we'll get a negatively curved surface. These two methods for changing the surface curvature have appeared in SIGGRAPH previously. The irregular spacings between the beams and eggshells force the structure to pop into 3D during the expansion deformation. In the weaving paper published by Vector and colleagues, they find a triaxial weaving pattern using straight ribbons with automatically inserted singularities. A third method to introduce curvature is to exploit the second term here. If we take this hexagon module and decrease the geodesic curvature of each ribbon, the patch will have positive curvature. If we increase the geodesic curvature, then the patch will have negative curvature. Compared to the previous two methods, changing the ribbon planar shapes changes the 3D curvature smoothly. Recently, a group of mechanical engineering researchers at EPFL, including two of my co-authors, applied this principle and created some simple woven shapes. They manually designed ribbons composed of straight lines and circular arcs, and showed that the shape approximation with these ribbons are better than using straight ribbons only. In this project, we want to optimize over ribbons of arbitrary curvature. This expansion in design space will increase the difficulty of the optimization problem, but it allows us to create previously impossible woven geometries. An important element that's missing from the existing work on designing woven structures is to incorporate physics-based simulation in the design process. An assembly of ribbons are able to form interesting shape without any external support because of the complex interplay between the elastic behaviors of the ribbons and the contact forces between them. We accurately track the equilibrium states of the ribbon assembly so that our optimized structure will settle reliably back into the predicted shape, even after extreme deformations, as shown in the videos here. I'll briefly describe how our simulation framework works. We model the ribbons as discrete elastic rods. Using this model, we can efficiently compute the stretching, bending, and twisting energy of the ribbons. To model the contact forces between the ribbons and implicitly constrain them to lay flat on top of each other, we parameterize each crossing by a set of reduced variables to efficiently constrain the two crossing ribbons. To construct such an assembly of discrete elastic rods and crossings, we take an embedded graph as the input weaving pattern. Our algorithm will automatically pair up edges to trace our ribbons and initialize them to be straight. We can specify the ribbons to have spatially varying stiffness by changing its cross sections. If we now try to find the equilibrium states of the initialized structure by minimizing the total elastic energy in all the ribbons, we'll see that the result is really not ideal. In particular, the ribbons have lots of twisting and buckling, and the crossing experiences high stresses. This is because currently, this structure, all of the ribbons are straight, and this topology has no singularities, so it really cannot conform to the target 3D curvatures. So what if we bring back the topological singularities? Alison actually created this model before this project started. She inserted the singularities based on her intuition, and I think it's actually quite amazing that it's possible to weave a Klein bottle with straight ribbons only. But as you can see, the shape is not smooth because topological singularities are inherently discrete and causes curvature concentrations. So let's see the results with the final remedy of using curved ribbons. This is the model found by our optimization. It approximates the target shape much better, and we didn't need to add any singularities to the topology. We find this solution by numerically optimizing over the ribbon's breadth shape. I discussed the details about solving this optimization problem in my SIGGRAPH talk, and I encourage you to check it out if you're interested. Now I will move on to some discussions about the fabrication process and the results. To facilitate the weaving process, we engrave the crossing numbers on the physical ribbons during laser cutting. And we also provide a visualization app where the user can interact with the 3D model and select individual ribbons or crossings. During the assembly, we used some temporary pins to fix the ribbons. Once the weaving is done, we only need the pins at the boundary crossings. We adopted the good habits of our colleagues in mechanical engineering and systematically validated our inverse design method by scanning and reconstructing the physical models. If you're interested in building some of these models yourself, you can also find the laser cutting files for the 11 physical models we fabricated in our supplementary material. In order to demonstrate that using curved ribbons allow us to continuously control the woven shape, we created a fun example where we morph a sphere into a cat without changing the topology of the weave. We hope that this can one day be used in designing transformable structures where you can achieve different 3D shapes by controlling linear elements only. Using curved ribbons also allow us to have different topologies for the same target shape. The benefit is that designing the topology becomes much easier. We can use many existing meshing tools to create inputs for our framework. A very interesting future direction is to incorporate the design of the topology in the optimization framework. An ideal result would be to have an interactive tool where the user can edit the topology and get quick feedbacks, such as here are the 5 best locations to place a singularity. Lastly, I want to discuss the main limitation of using curved ribbons. So far, we haven't been able to fabricate curved ribbons using natural materials. The fiber direction in bamboo, for example, prevents us from directly laser cut a curved ribbon out of it. Even when we use paper, plastic, or metal sheets to fabricate the ribbons, curved ribbons doesn't pack as nicely as straight ones. One possible solution for this problem is to apply a sparsity regularization term on the curvature variables so that the ribbons can still be curved, but maybe it's composed of very similar looking segments. We definitely need to study these problems more when we want to build large-scale structures using curved ribbon weaving. I would like to thank all my collaborators on this project and our funding sources for supporting our research. And thank you for listening.
Thank you, Samara, for the very interesting talk, especially the morphing example. I love it a lot. Yeah, and thank you again. And as usual, we will proceed to the talk about headliner and have a joint Q&A at the end. So yeah, thank you. So, and now it is my great honor to introduce our headliner, Jing Ren. So she's a PhD student at KAUST, supervised by Professor Peter Wonka and Max Ovsyannikov. And she's a leading researcher in computing shape correspondences. And I met her in person about like 2 years ago when I visited her lab in France. But back then, when I read her work called BCICP, I was really impressed by the result of the paper. And I thought, okay, this Jing already nailed this research problem. I shouldn't be working on shape correspondences anymore. But I was like totally wrong. Like since then, she keep improving, and the state-of-the-art method she developed every year published many great works in SIGGRAPH, SIGGRAPH Asia, or SGP. And these days, she even started to explore very challenging problems like exploring the space of maps. So, and I believe Jing must have a lot of stories to talk about, especially on how like she beats her own methods. So without further wasting her time, let's welcome Jing.
Thanks, Derek, for the nice introduction. And thanks to all the organizers. Let me first share my screen now. I hope you can see my screen now. So if not, please let me know. Okay. My topic today is non-rigid shape matching via functional maps. So in this presentation, I will first give a brief description about the shape matching problem we want to solve. Then I will just like briefly introduce the functional map pipeline that we used to target like solve this problem. Then I will mainly like discuss 3 research projects that fit into the functional map pipeline that I participated during my PhD. So shape matching problem is a very fundamental problem in computer graphics, and it has a lot of applications. And the shapes we are dealing with are discrete triangle shapes, like the 2 human shapes shown here. And the goal of shape matching is trying to establish point-wise correspondences between the input shapes. And we would like to find some meaningful and like especially semantically meaningful correspondences between 2 shapes. So for example, here, we would like to map the vertex x1 on the male model to the vertex y1 on the female model. And similarly for the vertex on the body and on the legs. So these are the types of meaningful correspondences we would like to establish automatically. And here we use the color transfer to visualize the correspondences we computed. So for example, if two vertices, they are corresponding to each other, we're gonna assign them with the same RGB color. That's the way we visualize the correspondences. So shape matching, it has a lot of applications. So for example, we can use the correspondences we computed to transfer the motion or facial expression from an actor to some movie character, like the one shown there. And also we can use the correspondences to transfer texture from a tiger to a kitty, or from a zebra to different animal shapes, or even human shapes. Another application of shape matching is to perform shape difference analysis. So we can imagine that we can first compute the correspondences between a standard teeth model, like the one I'm showing here, and also between a scanned teeth from a kid. Then we can try to measure the difference between the standard model and the scanned model to kind of locate the unmatched regions. So perhaps this can help the dentist to come up with some plan to correct the overcrowded teeth. Another application for shape matching is shape retrieval. So we can use the correspondences we computed to define a similarity metric. So in this case, we can try to find the most similar shape from a large collection to the query shape. So we already mentioned some possible practical applications that shape matching can be helpful. So now the question is, how can we compute correspondences between input shapes automatically? Existing methods can be categorized into 4 main categories. So the first category is a point-based methods. So this type of methods, it tries to design some energy defined on pairwise vertices on the shape. For example, it tries to find the correspondences such that before and after mapping, the geodesic distance can be similar to each other. So something like that. Another category of shape matching method is parameterization-based methods. So for example, here, if we want to find the correspondences between the 3 status shapes directly, it can be really hard. So in the very beginning, as a first step, we can first try to parameterize these 3 shapes into some canonical domain, such as the gray region shown here. And estimating correspondences in this canonical domain can be relatively easy. So after we get some estimated correspondences in this domain, we can try to propagate back to the original shapes, by map composition, for example. We can also use the optimal transport to formulate the shape matching problem. So for example, we can think of a shape as some kind of distribution of 3D points on the surface. And we can then formulate the shape matching problem as trying to transport a distribution of points on the source shape to another distribution defined from the target shape. So in this case, we can use the domain knowledge in the optimal transport to solve the shape matching problem. So in this presentation, I'm gonna focus on the functional map pipeline. So this type of technique, it tries to find the correspondences between functions defined on the shapes instead of trying to find the correspondences between vertex directly. So I will first give a brief introduction how to compute a functional map, then I will just discuss different projects in more details. Let's first start with the most commonly used shape registration method, iterative closest point. So assume that we have 2 pandas that we want to register, and also assume we are given some kind of correspondences, but it's in a very poor quality. For example, there's a vertex P on the blue panda, and it's mapped to the head of the white panda. So we want to register these 2 pandas in 2D, and also we want to improve this kind of correspondences. And the ICP scheme, it tries to iteratively improve these correspondences in the following way. So we first use these initial correspondences to compute a rigid transformation, which includes a rotation matrix R and a translation vector T. And once we have this rigid transformation, we just apply it to the blue panda. So we can see now these 2 pandas, they just better align to each other. Then we can just use the nearest neighbor search in the spatial domain to update the correspondences. Now we get better correspondences. So we just do this scheme iteratively. We try to solve for some rigid alignment. And after the 2 shapes, they are better aligned, we update the correspondences. And this iterative procedure, can be used to minimize the energy shown on the top. So here, x1 and x2, they are the vertex positions for the two shapes. So we can see that this energy, what it tries to do is that we hope that the two vertex, if they are corresponding to each other, their final position after this rigid alignment should be close to each other. So this is what this energy tries to formulate. So we just use the procedure we just described to minimize this energy. And we can imagine that for this two panda case, after a few iterations, we can get better and better alignment. However, this simple procedure does not work for non-rigid shape pair, such as the two humans I'm showing here. So even though we can find some reasonable rigid alignment for these two shapes, it does not make too much sense to apply nearest neighbor search in the spatial domain. So for example, for a vertex of the male model on the shoulder, its nearest neighbor in the spatial domain would be a vertex on the hand or on the arm of the female model. So the reason why the standard RCP I just described does not work in this case is that the vertex positions that ICP tries to register, they are extrinsic features of the shapes. So a direct solution to fix it is to try to align some intrinsic features of the shapes. So we can like, so the intrinsic feature is going to be like more stable, so we can apply them in the non-rigid shape pairs. So that's the goal. So actually, we can find some intrinsic features directly. We just need to define the Laplace Beltrami operator on the shape delta, and we just like apply the eigen decomposition to this operator delta, and we can get a set of ordered eigenfunctions with respect to their non-negative eigenvalues. So here I show some small subset of eigenfunctions on the human body, and each of the eigenfunctions is actually just a per vertex function defined on the shape. And the most important thing is that these eigenfunctions, they are actually ordered. So they are corresponding eigenvalues. Sorry, yeah, corresponding eigenvalues, they are also sorted. It can be this actually encodes the frequency information of the corresponding eigenfunctions. So we can use each of the eigenfunction as some kind of descriptor to describe the vertex on the shape. So more specifically, assume there's a vertex P on the shape, and we can just collect the values of different eigenbases at this vertex P, and we just like group them together as a vector. So now this is an intrinsic vector we're gonna define at this vertex P. So in the standard case, standard ICP case, the feature we're gonna use, they are just XYZ coordinate at this vertex. But now we do not use the vertex positions, we are using the values from the eigenfunctions. So we can easily generalize the spatial ICP to the spectral domain. So here's the energy we already discussed, where the x1 and the x2, they are the vertex positions from the source and the target shapes. And we want to find the 3D or 2D rotation matrix R and the translation vector T to try to register the vertex positions from the two shapes. So as we just discussed, now we have better and intrinsic features for the two shapes, which are the eigenfunctions of the two shapes, phi1 and phi2. So now we can just modify this energy a little bit. So now we have another rotation matrix C. It tries to register the eigenfunctions from the two shapes. And this rotation matrix C should be high dimensional, since the since the eigenfunctions we're going to use can like have from like 100 or 200 or even more. So we can see that this rotation matrix is no longer a 3x3 rotation matrix, but a high dimension rotation matrix. So we can just like visualize this as a matrix shown here. And since we know that this rotation matrix C, it tries to register the eigenfunctions from the two shapes, and also the eigenfunctions of the shapes usually can be used as some kind of basis to represent functions defined on the shapes. So in this case, we can regard this rotation matrix as a functional map to transport the coefficients of the functions like projected into the eigenfunctions. So that's why we're going to call this high dimensional rotation matrix as a functional map. So now the question we have is, how can we compute such a functional map from scratch? Here is a standard pipeline to compute a functional map. So we can first use some existing methods to compute some shape descriptors, such as a wave kernel signature, shop descriptor, or heat kernel signatures. So we just use these kind of existing methods and compute a small set of descriptors defined on the shapes automatically. And then we can design some functional map energies from the descriptors we just got and other geometric constraints such as bijectivity or isometry. So now we have some kind of energy defined on the functional map C, which is a matrix. Now we can just use some existing continuous solver to minimize this energy, and we get an optimized functional map. In practice, this optimized functional map can have some like errors or local distortions, whatever. So usually we need some post-processing method to further improve the accuracy or the quality of the functional map. Then after we get some refined functional map, we can use it for different applications. For example, we can use it to transfer segmentation, to transfer motion, texture, or just like apply shape analysis, even collection. So the three projects I'm gonna discuss also fits into this pipeline as well. So the first project I'm gonna discuss, in this project, we propose a new functional map energy. So it's a new regularizer. It can be plugged in the commonly used functional map energy. And this newly introduced energy can help guide the optimization process towards a map that is more orientation aware. The second project is what we call zoom out. It's a new refinement method. It can be used to efficiently improve the quality of any given correspondences between a shape pair. In the third project, we want to just go through the complete process where we want to systematically explore and investigate the search space of a given shape pair. So now I just gonna introduce each of the project in more detail. So the first project is about orientation aware operator. So orientation is really important because we have this problem that like we start this functional map pipeline from some pre-computed descriptors, and most of these descriptors, they are intrinsic, which means it's hard for them to disambiguate left from right. So for example, here I show a pair of wave kernel signature human shapes, and here the color red means that the value of this descriptor and this vertex is high, and blue means lower value. So we can see that for this highlight vertex, if we just want to find its nearest neighbor, according to this computed wave kernel signature, it can either give you this vertex on the right arm or on the left one. So we can see that these kind of descriptors, they have this symmetry or orientation ambiguity. And this is something we want to avoid. For example, if we just take these descriptors as input and use some the previous functional map pipeline, we can usually get a map that some region gets mapped to left and some region gets mapped to right. So we have this mixed symmetry. So we really want to avoid this. We hope that we can get a map has consistent orientation. For example, left is always mapped to the left part, or the left part is always mapped to the right. We want to avoid this mixture of left and right. So how to do that? Let me first give some definition of the map differential. Assume we have a pair of shape S1 and S2, and also some smooth map T, which maps a vertex P to the vertex Q of the second shape. We can define the map differential from this map T, where this map differential, it tries to map the tangent plane at vertex to the tangent plane at the corresponding vertex Q. So our observation is that if a smooth map T is orientation preserving, if and only if its map differential is orientation preserving, we're gonna show that it's much easier to describe the orientation using the map differential instead of using the map directly. We can assume that we already have some kind of map differential. So now we can just construct a pair of non-parallel tangent vector W and V at this vertex P. Then we just use this map differential to transport these two tangent vector, and that's how we get the dt of W and dt of V. So they are the two tangent vectors on the second shape. So now we can use this tangent vector and the normal vector to form some local frame. So these are the two local frames at vertex P and vertex Q. If the map differential is orientation preserving, it should preserve the direction of the local frame of the two corresponding vertex. And here the orientation of the local frame is just simply if this local frame is right-handed or left-handed. So what we need to do is just to quantify whether this local frame is right-handed or left-handed. This can be done easily. So we just need to take the outer product between the two tangent vector and just to check if it's gonna in the same direction with a normal vector. If so, it should be a right-handed local frame. Otherwise, it should be a left-handed local frame. So in this case, we know that if the map differential is preserves orientation, these two local frames should be in the same orientation. So if we just take the outer product between the two tangent vector and then take the inner product with a normal vector, this scalar value should have the same sign between the two local frames. So this gives us a way to quantify the orientation of the local frame. So how can we use it in the functional map pipeline? So in practice, we don't have such a map differential to construct local frame. So in our paper, we propose to use descriptors to construct local frames. This is how we do that. Let's assume that we are given a descriptor f, and this f is pure intrinsic, and it gives exactly the same value at vertex P and vertex Q that are symmetric in this shape. We can take a look at the normal vector at these two vertex. Now we just take the gradient of this descriptor at these two vertex. That's how we get the gradients. It's two these are the vectors defined at this particular vertex. Now assume we have another function g, and this descriptor g is different from descriptor f, and also this g is symmetric. It gives same value at vertex P and at vertex Q. So similarly again, for each of the vertex P and Q, we have three vectors, two gradient vector and one normal vector. And we can use these three vectors to construct a local frame. And now we just need to check the orientation of the local frame as what we did before. If we take a look at the local frame formed at vertex P, again, we just take the outer product between the two gradient vector and then check if it's in the same direction with a normal vector. In this case, we can see that yes, they are in the same direction. It shows that at vertex P, we get a right-handed local frame. Now, if we look at the vertex Q, we measure it again. Now this cross product between the two gradient vector, it's in the opposite direction with the normal vector. So we can see that even if the input descriptor f and g, they are symmetric and they cannot disambiguate vertex P and vertex Q. It gives exactly the same value at these two vertex, but still we can introduce some extrinsic information by using the normal vectors and take the gradient of the two descriptors. So in this way, we can construct a new descriptor. This new descriptor is not symmetric. It tells us the left is different from the right. So in this way, we can encode the orientation. We can extract non-symmetric information from symmetric descriptors. So in the paper, we can find more details how we formulate and discretize this formulation, formulate as an orientation operator and put it into the functional map and pipeline as additional regularizer. So yeah, I think this is the main idea of this description of this operator. Also in the same paper, we propose a new refinement method called BCICP, short for bijective and continuous ICP. So this method, this refinement method is purely heuristic. We just try to promote the bijectivity or continuity of the input chips. So we combine this new regularizer to promote the orientation together with a refinement method. We just apply it for shape matching and check it on the Faust and Tosca dataset, and we compare it to the existing methods for shape matching. It shows that our new method, it's indeed better promotes the orientation of the maps, and it's also improves the accuracy of the computing point-based maps. So this is a collaborative work with Altlian, Peter, and Max. Yeah, so this is a first project. The second project I'm gonna discuss is called zoom out. This is a refinement method. So it's just like assume some kind of initial correspondences is given, and we just want to improve the quality of the given correspondences. So we have discussed this spectral ICP before, where we want to find a functional map C to align the eigenfunctions between of the two shapes. So that's the phi1 and the phi2. So similar to the standard ICP, this energy can be minimized in an iterative way. So we just from the given initial correspondences, we can first solve for a functional map that can be used to align the two spectral domain of the two shapes. And then we just apply nearest neighbor search in the spectral domain. That's how we get the point-based map. Then we just repeatedly just update the functional map and then solve for the point-based correspondences. So this should be efficient and should be effective, but still it's not perfect. The reason is that this phi1 and phi2, the intrinsic features we used, it can be large, for example, up to 200 eigenfunctions we want to register. In this case, the functional map we are solving for is the 200 by 200 matrix. So we have a lot of variables to solve. But in the very beginning, the information we have is just a very sparse landmarks or a very small set of descriptors. So in that case, the complete system is underdetermined. So we are trying to solve for a large amount of variables from very limited input information. So in this case, it's very easy to get trapped into some local minimum. So the goal of this project is to still minimize this energy as it is, but we would like to avoid some undesirable local minimum. Let's first give some intuitions about our method. Let's assume that now we have a pair of 3D panda to align. So if we start from a really bad initialization to align this 3D panda, it's really easy to get trapped into a very bad local minimum. For example, the 2 years, they're orthogonal to each other. In that case, it's really hard to jump out of that local minimum. So if we want to avoid that bad local minimum, it would be better if we just do the registration in a global to coarse to fine this kind of fashion. So more specifically, we can first try to align the body of the two pandas. And once they are properly aligned, we can try to rotate the blue panda a little bit to register the head. And once the head and the body of the two pandas, they are properly aligned, we rotate the blue panda again to try to align their ears. So in this case, we are just trying to register the two pandas, first register the global structure and then to the local structure. So I think this registration process is very natural. It can also help us to avoid the undesirable local minima I described before. So if we look at the eigenfunctions of this panda, so here I show some subset of it. So we can see that actually the eigenfunctions, they already encoded the frequency or the structure scale of the shapes. It's already encoded into the eigenfunctions. So for example, when in the first few eigenfunctions, these eigenfunctions, it has low frequency, which means they have a small number of a small value of the eigenvalue. So these high frequency features are mainly defined on the body of the panda. And once we moves to higher and higher frequency, gradually we started to have more local features defined on the head or on the ears. So this told us that the eigenfunctions we want to register, it has a very nice property that it's already ordered according to their frequency. If we have 100 eigenfunctions, we want to do the alignment, we do not need to do them at the same time. We can first try to align the first few eigenfunctions, just as what we did to align the body of the panda first, and then we just introduce higher and higher frequencies and do the alignment. So this is just the kind of the same procedure we did, try to align the body and then move to the head and then move to the ears. So that's intuitions of our method. So the complete algorithm is super trivial and super easy. So like we assume that some correspondences are given in the very beginning, and we just start from a really small functional map. And this small functional map, it just tries to align the first key eigenfunctions of the two shapes. And once the first k eigenfunctions, they are properly aligned, we can find the nearest neighbor in the spectral domain to update the PointBased map. And then we just increase the feature space, like by 1 or by any number you define. So now we include more and more features inside, and we go back to step 2 again and try to align a larger set of eigenfunctions. And with the fact that the first few eigenfunctions has already been like pre-aligned. So in this case, we can avoid a lot of like undesirable local minimum. And the complete algorithm is more like efficient, and also it's more stable. So if you can see the video I show on the top, on the bottom, we can see that this functional map in the red rectangle, it's just get larger and larger over the iterations. So we're just like trying to include more and more eigenfunctions to register. Yeah, super easy algorithm. So here's a qualitative example. Now for the shape pair of the human shapes, they have like super high resolution. And if we want to like establish some dense correspondences between the two shapes, we usually like first do some samples to save some time. So here we just like sampled 5,000 vertices on the source and the target shapes, and we just apply different refinement methods, and we just visualize the computed correspondences by texture transfer. We can see that in this case, both BCICP and this zoom out method gives reasonable correspondences. But we see the zoom in view, we can see that the zoom out method gives like preserves the local region better than BCICP. Now, if we further decrease the number of samples, we can see that like the zoom out still works well. I mean, at least better than the other two methods. If we like compare this zoom out method to the existing shape matching refinement method, we can see that this method is super fast. And also it's very easy to implement, as we see that it's just 5 lines of code. And also it achieves state-of-the-art accuracy for shape matching. And it can be like scaled to high resolution meshes and even point cloud, because we can use some existing methods to estimate the eigenfunctions on the point cloud. This is a like joint work with Simona and Emanuela, Avishek, Peter, and Max. Okay, and in the previous discussion, our goal is trying to find a single or refining a single map for between a shape pair or a single shape. But in practice, usually like multiple maps can exist, like multiple reasonable maps can exist at the same time. So here I show an example where for this source shape, I try to find a self-symmetric map from the source shape to itself. And I just run some existing methods. We can see that like different methods gives very different maps. And each of the map, they encode like different symmetry of the shape, and all of them, they are reasonable. So for example, we have this back to front map, and also like where the you can see the belly is mapped to the back. And then for the second map, it's a direct map. So it's basically, in this case, it's just an identity map. Then for this map, we can see that for the third one, we can see that it both map the back to the front, and also it maps the left of the human to the right. For the last column, we can see that we got this mixed symmetry on the top body. It's just like back to front, and then in the lower body, it's just left to right. So we can see that all of these maps, they make some sense. And there's another example. We have a pair of human shapes, and we just run the zoom out method we just described from different initialization. And again, we get very different maps for this shape pair. And all of them, they make some sense. So we have this question that is it possible to compute multiple reasonable maps between a given like shape pair or a single shape? Let's first get a sense of the complexity of the map space we are dealing with, like for the shape pair we just like described. So for this shape pair shown on the bottom, we first sample 10,000 PointBased maps, and then we just use multi-dimensional scaling to embed this 10,000 maps into 3D, and then we just like evaluate the commonly used geodesic distortion energy on these sampled maps. So we can show the landscape and also the contour of this energy. We can say that this energy, this landscape is super complicated and it has a lot of local minimum. If we take a look at the local minimum, like the most prominent for local minimum of the landscape for this geodesic distortion energy, they are the 4 maps we just showed before. Here is another visualization of the maps. So we just like transport the spot function defined on the shape, and then we can visualize how this spot function get mapped with respect to the corresponding PointBased map. So we can see that it definitely makes sense that for a shape pair or even a single shape that multiple reasonable maps can exist. So it would be like very natural to think about this problem that can we extract or can we find or explore the search space in some way so we can extract multiple meaningful PointBased map at the same time. So if we just like, otherwise we can just like use a previous method and can get a single map in a random way, but we don't want this. We just want to have multiple PointBased map at the same time. A naive solution for this problem, that's to find multiple meaningful and distinctive maps in the map space, would be clustering. For example, we can do it in this way that we just sample a lot of PointBased map in the map space, and then we just like cluster the sampled maps, and we return the cluster centroids as the like the final maps we want to have. So this can guarantee that the returned maps, they are distinctive enough from each other, but this naive solution does not work because in practice we don't know like how many number of symmetries or like how many like meaningful maps gonna exist for the given shapes. So we don't know like the number of centroids for the clustering to work, and also it's not guaranteed that we can uniformly sample from the map space, which means we can easily miss some important PointBased map in the map space. And also it's not clear, like given 2 PointBased map, how can we know that if they are similar to each other or not? And also if they are similar to each other, which one should we keep? So in this case, like this naive solution does not work. So in this, in the search project, we propose a tree structure to like systematically explore and investigate the search space. We use the functional map as a map representation, and we organize the PointBased map into a tree structure, and this tree expand along the frequency domain. So so this algorithm, it's like in this algorithm, we just like define the rules to grow the tree and also to prune the tree. And at the end, once we terminate the growth of the tree, we can return the node, and each of the node, it just represents a map. We just return the node that is not terminated as a output. So in this case, we can just like output multiple maps at the same time. So here's an algorithm of our method. We always start from the smallest possible functional map, which is just a 1-by-1 functional map. And this is fully determined by the constant function, constant eigenfunction of the 2 shapes. Then we just grow this functional map along its frequency domain by enumerate all possible mappings between the eigenfunctions that's in a similar frequency. And in this case, the tree can be like grown very fast, and it can be like very fastly become like intractable. So we need to also like prune the tree and only explore the good ones. In this case, we can use some like commonly used functional map energy based on some geometric constraints to determine if a node, which is just a functional map, if it's good or not. If it's bad, we just like remove it. And also in this case, sufficiently different maps is well defined. We just check if the 2 functional map which are just two matrices, they are close to each other or not. So this algorithm, it just looks like this. And as a result, this map tree algorithm, it can output multiple maps for a given shape pair or a single shape. For example, for the human shape pairs, we can compute 4 maps, which are the direct map, symmetric map, back to front, and also the double flip map we showed before. And the same thing for the human and the gorilla shape pairs. And also we can output 2 meaningful maps for animal shapes like dog, cats, lions. And for some man-made objects with multiple symmetric axes, we can output more than 4 maps. And this work is collaborated with Simona, Max, and Peter. Here we can see qualitative results, like we have this object shown in the middle, and for each of the components, we just run our map tree algorithm to try to detect like multiple self-symmetric maps. For example, in the top row for this particular component, we can find all the rotational and reflectional self-symmetric maps. So by running this algorithm for different components can help us to understand for example, the symmetry group of the input shape. Here's another example, like for this knot. Actually, it should have like infinitely many self-symmetric maps. Using our algorithm, we can output like a few hundred of them, and all of them, they are smooth and meaningful. But if we just run the previous method, we can only output a single map. And in this like challenging case, it's like the map is not continuous enough. So, short summary. So into this talk, I discussed like 3 projects in the functional map pipeline. The first project is about introducing the orientation preserving operator into the functional map pipeline so that we can get a better, like a point-based map with more consistent orientation. The second project is about zoom out, which is a refinement method. It can efficiently improve the quality of the given correspondences. For the third project, we propose a map tree algorithm which organizes the point-based maps into the map space in a tree structure, which can help us to like obtain multiple meaningful maps at the same time. Okay, that's all. That's the end of my presentation, and thanks for your attention.
Thank you, Jing, for the great talk, and also thank you both. Actually, thank you both for the great talks. So we will now start our joint Q&A session. And in the meantime, if you have additional questions, please feel free to post them on YouTube or on our Discord. And yeah, and I will start with a question for Samara. So, and this is an interesting question. Like, is it possible to have a single very, very, very long kind of ribbon to wrap around the object, or instead of having like multiple separate ribbons, is it possible to have a very, very long single ribbon?
Yes. If we do not care about ribbon self-intersection in the plane and the laser cutting machine wouldn't fit this ribbon or anything like that, there are topologies where when you trace out the ribbons, it's really just a single connected one. And from our experiments, so we have different ways to generate the topology. Some of them are done by our in-house architect. He manually designed some of the topologies. And we can also use some existing meshing tool to compute the dual graph and use that as a topology. And we find that if we use existing meshing tools and find the dual graph in this way, often there are very few ribbons in the mesh. So we have examples with like 3 ribbons. One of the duck actually have only 3 ribbons. Yeah, so it's possible. We don't have a specific way to use that as a goal to design single ribbon weave yet, but there are examples.
Yeah, that's very cool. And actually, when you brought up the initialization part, it also leads to another question from the audience: is that how important is the initialization? Is it possible for the method to change the topology of the ribbon during optimization?
Mm-hmm. Right. So we currently cannot change the topology during optimization. We only adjust the ribbon shape and the crossing positions, all of those parameters, but the topology is always fixed. And this could be advantage or disadvantage, depends on the end application. In terms of the initialization, because curved ribbon really enlarge the design space a lot, our initialization process is quite simple. as long as the input crossing positions are on the surface, we haven't really encountered an example where we couldn't find results for an input topology.
Well, that's great. Okay, and the next question is for Jing. So if we only focus on like a single class of shape, like humans, is it possible that we can do a better job if we leverage the similarities among those shapes instead of assuming the input surface like a very general shape?
Yeah, definitely. Like for sure, like if the two shapes are like all human shapes, it's definitely like easier to compute the correspondences, because like for most of the not most of the humans, we can assume the near isometry, and in that case, like if the assumption like satisfied, like the eigenfunctions can be aligned, in that case, definitely we can get better correspondences.
I see. So perhaps like if we are staying in the same class, then we can kind of impose those kind of isometry assumption, and then adding further regularization or additional tools that we have for the isometric shapes.
Yeah, definitely. We can just like design these specific regularizers into the functional map energy for the specific task. Definitely.
Okay, understood. Okay, and the second question is for Samra, is that for the Klein bottle or other surface that have self-intersection, does the method automatically find the strip which pass through the holes, or is it actually a happy coincidence?
Right. So no, it doesn't. Well, because our input topology is nicely putting the Klein bottle back to the hole to itself. Yeah. We don't have a collision terms at the moment to prevent the ribbons from not self-intersect when it's not adjacent ribbons. So no, it's based on the initialization.
Okay, I see. I understood. Okay, and the next question is for Jing. So, and actually this is for the orientation aware functional map, and is the orientation energy robust to like the different poses of the humans, or could there be a pose where the orientation term cannot discriminate like intrinsically for like similar parts in the shape?
Definitely. So it can happen. So that's a quick answer. So it can happen that you can see that like in the third project, we show 4 different like maps. So in that case, the orientation can only tell 2 from the other 2. So which means the direct map and also the double flip map, if we just take out the local frames, they have consistent like orientation of the local frames. So in that case, this energy cannot disambiguate this direct map and the double flip map. But for the other category, it should be like stable enough.
I see. Then perhaps it leads to another question that also from the audience, that potentially is more from like practical use case. Like, is it better to, for example, use some refinement method to kind of correct the error of the orientation part, or is it actually better to kind of just explore the space of maps and just having all these results available and then perhaps choose the one that has a correct orientation?
Actually, I definitely like using the map tree method is going to be easier since it's automatic. So, and also like we find that we can like, if we have a large collection of strips, we can use this like information from the collections to help us to select which map is better. So we also like propose a selection method in the paper to select like the most, we assume the desired map from the multiple of them. And I think like the successful rates should be something like to 80 or 90%. So should be okay. But definitely it's also possible that we can use some extrinsic information like the XYZ coordinates to find it. If like the scan shapes, they are kind of like pre-aligned, they are standing on the floor. So it definitely can help us to like the extrinsic information can be more stable than like we have some random shapes in the space, I think.
I see. And this leads to another follow-up question also from the audience, is that like, do you think like actually the functional map as like technology you have been working on so far is ready for like deploy to like industry? Or still have some like big challenges that we need to solve?
I think it's definitely application like specific. So I think the current functional map pipeline is ready for finding some stable initial correspondences. But if the downstream applications need like for example, we want to preserve some local details, some structured lines, or some mesh topology. So these kind of regularizers, they are currently not considered into the functional map. But if the per vertex correspondence is all you want, I think should be stable enough.
I see. Okay, thank you for the answer. And next is a question for Samra, is that we're wondering whether we have like experience like demonstrating your tool to like the professional artists who are doing like 3D weaving. Then if yes, then to what extent the output of your optimization like match their intuition?
So far we haven't done that yet, but I did receive a request recently of using this tool to design something. So we're in the process of working on that. And I'll update you when we have more.
Well, that's really cool. I'm really looking forward to like hearing what their feedback of your great method. And another question actually related to like make this actual design tool is that is it possible to incorporate some, for example, like curve constraints or other artistic controls in your method? For example, like in vector field design, we will typically put some curve constraint on the surface. It's possible to do the same thing on your method?
At the moment, no, but that's a very interesting future direction. It's related to the points where we want to add more regularization or more control on how the ribbon is curved. Maybe arbitrary curvature is not great and we want some artistic inputs. So right now, this is the future direction.
Okay. Oh, and another question that's related to this is about the singularity. So like, I believe like placing singularities is like a very important topic. For example, if you want to flatten a shape into 2D, and I wonder whether there's some difference in terms of the optimal singularities in your like 3D weaving and those kind of optimal singularities when doing like surface parameterization, or actually you can kind of use their method to determine singularity.
Yeah, at the moment we're doing the latter, that the meshing tools give us the singularity, we can directly use it. I think once we start having more regularization on the curvature, because right now the curvature can just be anything, and that really have lots of freedom that you can just take any singularity as long as satisfy the global topology constraint of the surface, that it will work. But once we have more, we want to have more control on the curvatures, then we also have more constraint on where the singularity should be.
Well, okay, thank you for the answer. And another question for Jing is that this is actually a very practical question. Is that there are a lot of functional methods and some of them are based on optimization like the one you mentioned today, but there are also other like machine learning based functional methods like supervised one or even unsupervised one. So if you want to use one of those tools in our own research, how would you recommend us to like choose among these methods?
I think this also depends. Like for example, if we have large enough data set for the learning-based methods, but I definitely think that for human shapes, the learning-based methods should be a very good direction since now we have more and more data sets, and also like the most like advanced functional map-based deep learning methods, it does not rely on the sim topology anymore, so it makes it really convenient to do. Otherwise, like still like functional maps still have a lot of like unsolved problems, like for isometric shapes and also with topological noise. So for this, because like, especially like with this topological noise, the very basic assumptions of we can't find such a rotation matrix to align, the eigenbasis does not hold anymore. So in that case, we still don't have a very good solution to handle these cases. So I think both direction worth researching.
I see. Thank you for the answer. And I know we still have a lot of questions that I didn't go through, and sorry for that. But because we are already over time, and please like keep posting questions or even like copy your question from YouTube to our Discord for some offline discussion. I believe our speakers are happy to answer questions offline. So for now, let's thank our speaker again. And also thank you everyone for joining this colloquium. And we also want to thank our artist, Peter Royer, for making the great poster for today, and see you all next week.